Welcome to The Explainer. Today we're opening a case file on a very mysterious threat, one that's targeting some of the foods you and I absolutely love.
All right, so let's get right into it. This mystery, it's playing out in fields all over the world. Now, you might look at this and just see a sad, dying plant. But what you're really looking at is a crime scene. And the culprit is completely invisible.
So to crack this case, first things first, we've got to identify our prime suspect.
And here it is. The culprit's got this long scientific name, Ralstonia solanacearum. Yeah, it's a mouthful. So let's just call it by the trouble it causes, bacterial wilt. This thing is a tiny pathogen that hangs out in the soil and water. Its whole MO, it gets inside a plant's vascular system, like its veins, and just clogs everything up. It basically cuts off the water supply, starving the plant from the inside out.
Now, this isn't some random attack. Oh no, this killer has a very specific hit list, and on that list are some of the most important crops we have on the entire planet.
And this is where it gets really serious. I mean, just look at this list. We're talking about the potatoes for our fries, the tomatoes for our pasta sauce, even peppers, eggplants, and bananas. This one little bacterium is a huge threat to all of them. And that, of course, makes it a massive risk to our global food security. It's no wonder this thing is public enemy #1 for plant health detectives.
Okay, so how do you even begin to hunt for an invisible killer like this? Well, for our plant detectives, it all starts with knowing exactly where and when to look for the clues.
The investigators, they're smart. They don't just look at the sick plants. They have to survey the entire scene. And because this is a waterborne pathogen, they zero in on high-risk areas. Think about places where water gathers or flows, like drainage canals or irrigation rigs. For this bacteria, that's like a superhighway, letting it travel and spread everywhere.
And it's not just about where you look. When you look is absolutely critical. Timing is everything. Inspectors hit the fields during peak growing seasons, right when the plants are most vulnerable. But here's the really clever part. They go out during the hottest time of the day. Why? Because that's when a plant under attack can't get enough water. And those wilting symptoms, they become super obvious. You just can't miss them.
All right, now we get to the really cool part, finding the actual evidence. See, this bacterium, it's sneaky, but it's not perfect. It leaves behind a very distinct trail of clues. You just have to know what you're looking for.
Let's take a potato field, for example. The first clue you might spot is the wilting plant. But the real damning evidence, that's hidden inside the potato. When you cut one open, you see this, a discolored brownish ring. That ring is the bacteria's trail, the path of the infection. It's a dead giveaway that the culprit's been there. And get this, it can get even more obvious. This just shows you how widespread the infection can get. In really bad cases, the bacteria multiplies so much that this sticky white ooze will literally start seeping out of the eyes of the potato. I know, it's pretty graphic, but it's undeniable evidence.
It's a similar story in tomato fields. The crime scene is just, well, it's stark. You'll see perfectly healthy, strong plants standing right next to ones that have just completely collapsed. And it happens fast. We're talking a matter of days. That rapid decline is a classic calling card of bacterial wilt.
But this right here is the smoking gun. It's an amazing, simple test you can do right in the field for immediate proof. An inspector just cuts a piece of the stem, sticks it in some clear water, and then they wait. Within minutes, you see these milky white streams flowing out. That's not plant sap. That's millions and millions of bacteria. It is absolutely undeniable proof.
So, once a plant is identified as a suspect, the job's not done. Now, the evidence has to be collected, and you better believe they do it carefully. It's all about following a strict protocol, just like at a real crime scene, to make sure nothing gets contaminated. And I'm not kidding, it really is like CSI. The inspector photographs everything, they carefully collect a tissue sample, and, this is so important, they sanitize their tools after every single sample. The last thing they want to do is become the spreader themselves, right? Then, the sample gets double-bagged, labeled, and it's off to the lab. Okay, so the evidence from the field looks pretty solid, but you can't officially close the case just yet. For the final confirmation, those samples have to go to the lab.
And back at the lab, the scientists bring out the big guns. They use all these advanced molecular techniques to get a 100% positive ID. This is what gives the final verdict. Once they confirm it, the authorities can spring into action and work on containing the outbreak.
So you might be thinking, why go through all this trouble? Why does all this detective work matter so much? Well, as the International Plant Protection Convention says, this kind of monitoring and surveillance, it's not just important, it's absolutely vital.
Because here's the bottom line. Every single time these plant detectives solve a case, they're helping to protect our entire global food system. They stop outbreaks in their tracks, they make sure it's safe to trade food between countries, and they keep farmers from losing everything. This work, this is what keeps food on all of our tables.
And it really makes you think, doesn't it? What other invisible threats are out there? What other silent battles are being fought every single day by these scientists and inspectors, all just to keep our world safe and fed? So if you had fun cracking this case with us today, do us a favor and hit that like button and drop a comment below. And of course, make sure you subscribe for more deep dives into the hidden science that's shaping our world. Thanks so much for watching.